If you move a distance of 0 meters in exactly 0 seconds, your speed in that moment will be 2 meters per second. The proof is simple and quick. 0 is the same as 1 minus 1, and because 1 is equal to 1 times 1, we can also square it. This form now has the advantage that we can apply the formula for the difference of squares to the numerator. So 1 squared minus 1 squared is the same as 1 plus 1 times 1 minus 1. And in the denominator we can factor out a 1. Now we can reduce the factor 1 minus 1, and what remains is 1 plus 1 divided by 1, which is 2. Surely something will seem wrong to you, but where's the actual error? You're probably convinced that this is where the error lies, because you've learned that you can't divide by 0. However, that's actually not correct. To really understand what division by 0 is all about, we first need to understand how math actually works. So let's cook it. Imagine math being a soup. What would be the key ingredients? Well, for one we need so-called theorems. These are true statements, although the truth must also be proven. A typical example would be the well-known Pythagorean theorem. Another important ingredient would be definitions. These prescribe the meaning of certain words or phrases. Definitions are neither right nor wrong, at most they are either useful or not. But perhaps the most important ingredient is what we call axioms. Similar to theorems, axioms are true statements, but they cannot be proven. Rather, they are simply accepted as being true. But why? See, the problem mathematicians have is that they work with things that don't exist as physical objects in reality. For example, numbers. A number like 3 doesn't grow on a tree or can be produced in a lab. Or have you ever held one in your hand? What you see on the screen is just a symbol we use to represent the concept of a 3. I could also use another symbol, or a word. Numbers only exist in our minds, and they are by no means to be taken for granted. Today, there are still cultures that have not developed such a concept. For instance, a tribe in the Amazon only has words for 1, 2, or many. But depending on the context, they also use the words for 1 and 2 to mean few and some. So what we refer to as natural numbers isn't really that natural. We should have called them imaginary numbers instead. Nevertheless, in order to work with natural numbers in a meaningful way, we somehow need to define them formally. Although a direct definition is not possible, we can at least describe them by their properties. More precisely, properties that make sense in our imagination. This is what the mathematician Peano did. He formulated 5 axioms that formed a formal basis for natural numbers. The first one stated that 1 is a natural number. We see that this axiom doesn't tell us what a natural number really is, it just says that 1 is one of them. Okay, let's add it. Moving on, every natural number n has a successor s of n, which is a natural number. So, since 1 is a natural number, it has a successor s of 1. And since this number is itself a natural number, it must also have a successor, and so on. Then he stated, 1 is not the successor of any natural number. So if there's no natural number that has 1 as its successor, we can consider 1 as a kind of starting point. The next one states, if 2 numbers have the same successor, they must be the same number. This axiom kind of makes sure that each number has its own unique next number, so we can line them up in a clear order. Let's also give each successor its own symbol. The last axiom is the so-called principle of induction, which in short ensures that the set we are constructing will contain all natural numbers if we keep adding successors. Now, there's no way we can set up an experiment to prove axioms like these true or wrong. Nevertheless, mathematicians around the world believe in them. But they don't accept any axiom without thought. As soon as someone comes up with better ones, the old ones are discarded. Peano himself later modified his axioms by making the number 0 the starting point. If you want to formulate axioms with as many followers as possible, you must ensure that they are minimal. The less we have to just accept, the better. It is also important that your axioms don't contradict each other, since we cannot believe in both right and wrong at the same time. And they must be meaningful. we must be able to make some use of them in mathematics. For instance, the Peano-Axioms can be used to formally define operations such as addition and multiplication. However, we can't deduce every property that makes sense in our minds from the Peano-Axioms alone, and since these operations don't grow on trees, further axioms were formulated, the so-called Field-Axioms. Any set that satisfies these axioms is then called a field. The first two are not very spectacular, they only ensure that we can add or multiply in any order. The third one is more exciting. It requires the existence of a so-called identity element. That's an element that doesn't change another one when you add it or multiply by it. In case of addition, we call this element 0, and in case of multiplication, 1. And the fourth axiom requires the existence of a so-called inverse element. For every element A, there needs to be an inverse element, which we symbolize with -a, so that their sum gives the identity element. The operation of subtraction follows directly from this axiom. This isn't a separate type of calculation, it's just the opposite or the inverse of addition. Of course, we often write this operation in a slightly shorter form, such as 6 minus 2, but what we actually do is we add the inverse element of 2 to the number 6. In case of multiplication, we also want an element A to have an inverse element, which we symbolize with a to the power of -1, such that their product is equal to the identity element. This is the birth of division, another operation that's not separate. It's the inverse of multiplication. So when we divide 6 by 2, we actually multiply 6 by the multiplicative inverse element of 2, which is 1/2. Such an inverse should exist for every element except 0. This is the reason why no one divides by 0. It's literally excluded in the axioms. But why? Well, remember when I said that axioms must not contradict each other? That is exactly what would happen if we didn't exclude 0, as we will see in a moment. For the sake of completeness, let's include the fifth axiom first. This one simply shows how addition and multiplication work together. Now, if we were to allow 0 to have a multiplicative inverse, let's symbolize it with 0 to the power of -1, then according to the fourth axiom, 0 times its inverse must be 1. But what do the other axioms have to say about this? Well, according to this axiom, we don't change anything when we add a 0 to it. And according to this axiom, 0 times its inverse must have an additive inverse. So we can also represent the added 0 in this way. The first axiom tells us that we can change the order. And according to the last axiom, we can now factor out the inverse of 0. Now, this axiom comes into play again and tells us that 0 plus 0 is equal to 0. What remains is 0 times 0 to the power of -1 plus its additive inverse, which according to this axiom must equal 0. Therefore, 0 times its inverse must be equal to 0, not 1. We end up with a contradiction, so 0 must be excluded. And all mathematicians accept this, because these axioms are really good and we can use the resulting abstract structures to describe real phenomena. However, no one is forcing you to follow these axioms, except perhaps schools or universities. So if you want to divide by 0, you can. You just have to formulate new and better axioms that make this possible and are so meaningful that mathematicians will follow those ones instead. Of course, you could also divide by 0 without formulating or following any axioms, but then you have to expect that you too will be excluded by mathematicians.